Don't start modeling yet. Before the mesh, before changing the solver setting, before the rainbow contours, there is a step that decides whether your FEA will be right or worthless. Because FEA isn't just a software skill, it's a thinking skill. A successful analysis begins way before you open the program. It begins with you. How you think, how you question, and how you judge. Hi, I'm Dr. Iman. Welcome to section 1 of FEA Done Right series at MechCADemy. In this section, we'll take a step back together and look at some big picture ideas. Things that can help us think more clearly, avoid common pitfalls, and make sure our analysis is both meaningful and reliable. We'll talk about the value of critical thinking, how to guard against cognitive biases, and why flashy graphics can sometimes trap even experienced engineers. We'll highlight the importance of theory and remind ourselves why statics and mechanics of materials still matter. Then we'll address mentorship and, most importantly, integrity. These principles aren't just helpful, they're essential. They'll form the foundation that everything else in this video series builds on. Let's get started. Here's the hard truth. Your brain is lazy. It's not your fault, it's biology. The brain is constantly looking for the most energy efficient path, often jumping to conclusions or accepting the first answer that seems good enough. But in FEA, good enough might sometimes lead to results that are completely misleading. That's why critical thinking is your first and most important tool. It's the habit of asking deeper questions, like, does this model truly represent the physical system I care about? Are my boundary conditions realistic? Am I solving the right problem or just the one that's easiest to simulate? And here is where it gets tricky. Even the best engineers, those with years of experience, can fall into traps set by their own mind. These traps are known as cognitive biases, systematic thinking errors that distort how we interpret data and make decisions. In FEA, recognizing and resisting these biases can be the difference between false confidence and real insight. You might think I'm careful, I double check my inputs, but that's not always enough. Because these biases don't announce themselves. They feel like intuition. They feel natural. Imagine this. You're crossing the street with a coffee in hand, headphones on, your mind half focused. You take a step without truly checking. Your brain filled in the gap based on experience. It wanted efficiency, not precision. And that's exactly what happens in simulations when we breeze through steps because it worked last time. Let's look at some of the most common biases that show up in engineering analysis, and especially in FEA. The first one I want to talk about is anchoring bias. We tend to cling to the first value we see, an initial material property, a load guess, a previous result, and unconsciously adjust everything else around it. This can trap your model in a flawed starting point. So what is the best defense against this bias? Always reevaluate core assumptions from scratch. Next bias I want to talk about is familiarity and fluency bias. This is a bit different. Here, the trap isn't the first value. It's what feels easy and familiar. You repeat the same mesh size, the same boundary conditions, the same element type because it works before and it flows. But smooth does not mean correct. Ask yourself, is this actually the right tool or right method for this problem? The third one is halo effect. Maybe a respected colleague or the textbook suggests a method and suddenly it all feels right. But remember, reputation isn't validation. Now, let's go to the fourth bias. The fourth one is optimism bias. It's great to feel confident. Your model is ready, the loads make sense, and you expect everything to run smoothly. That's a good sign. But even confident models deserve a quick double check. One simple technique is the pre-mortem. Before running the analysis, pause and ask yourself, if this model were to fail, what would likely be the reason? This shift in mindset doesn't dampen your enthusiasm. It sharpens your awareness. It helps you catch potential issues early, so your confidence is rooted in careful thinking. Now, the last one that I want to talk about is confirmation bias. Once you believe the model is right, you start hunting for proof and ignoring yellow and red flags. This is especially dangerous during post-processing. when you might subconsciously downplay unexpected results or cherry-pick plots that support your expectations. So before you simulate, try to predict the result, even a rough estimate. This builds physical intuition and creates a reference point for reality checks. But don't stop there. Bring a devil's advocate, someone whose job is to question your model setup, boundary conditions, material choices, and interpretation of results. Okay, there are many more biases, but among those, the ones we covered are most related to FEA. Now, let's focus on halo effect due to its special relation to FEA. In FEA, the results often look beautiful. Smooth stress contours, clean animations, perfect symmetry, and that visual appeal can be deceiving. Just like Venus flytrap. It's not the brute force that catches the prey, it's its elegance. Look at this contour plot of total deformation on this device that is called hydroformer. Is this colorful? Is it beautiful? Yes, it is. But is it correct? I can tell you, it's not. Now, let me show you the correct one. See the difference? So remember, just because your model looks good doesn't mean it is right. Beauty in FEA should never ever replace scrutiny. This is a very important message I have for you. Now, let's switch the gear. Let's talk about theory. Learning the theory behind FEA isn't optional, it's essential. It gives you confidence, helps you troubleshoot, and makes your model more than just guesswork with nice colors. But don't try to learn everything at once. You don't need to dive straight into nonlinear thermomechanical coupling or plasticity models on day one. Start simple. Walk before run. Let your knowledge of theory grow with your experience. That way, you won't drown in it. You'll actually use it. Oh, one thing I need to mention. We will also cover some theory in this video series. I'm sure you will learn a lot and enjoy. Now, theory has another form as well. Let's cover that too. I am talking about the theory behind the physics of the finite element model. You need a solid grasp of the fundamentals. Start with statics. Make sure you can draw and interpret free body diagrams. Can you isolate a part of your assembly and show all the boundary conditions on it correctly? Next, review mechanics of materials. Know how materials deform, how stress develops inside components, and when yielding or failure occurs. Without this understanding, you won't be able to judge whether your results make sense or not. But remember, skill in one area doesn't automatically translate to another. Being confident in structural mechanics doesn't mean you're ready to tackle heat transfer or fluid flow problems. Each domain has its own governing equations and unique behaviors. If you're analyzing thermal gradients or fluid dynamics, take the time to learn the underlying physics before setting up your model. Ultimately, effective FEA requires balancing theory and practice. Theory guides you in building the right model and interpreting results critically, and practice tells you what makes sense in the real world and what doesn't. Okay, enough about theory for now. Let's talk about an important resource that can help you in your FEA journey. I want to talk about FEA Mentor. Yes, if possible, find one. Someone you can bounce ideas off of, ask questions, and learn from their experience. A good mentor doesn't just give you the answers, they help you ask better questions. They have likely seen the pitfalls, the common mistakes, and the clever tricks that don't show up in textbooks. And having someone in your corner can accelerate your learning more than any manual or tutorial. There are many FEA experts out there, especially on LinkedIn. To have better access to them, connect with me on LinkedIn. Here's a QR code for my LinkedIn account. Take a look at the conversations happening on my posts. You'll find experienced voices sharing insights, ideas, and support. It's a great way to grow your network and learn from the community. Now, let's go to the next important item. I want to talk about integrity. Integrity means doing right thing even when no one's watching. In the world of FEA, that translates to honesty, transparency, and refusing to take shortcuts, especially when the pressure is on. Integrity shows up in small decisions we make under pressure. Let's be honest, Clients, managers, and stakeholders usually want good news. They want to hear that the design is safe, efficient, and ready to go. And that pressure can quietly push analysts to massage the model until the results match expectations. But here is the truth. FEA isn't about delivering what people want to hear. It's about showing what's actually happening. Your job is to report the truth even when it's uncomfortable. Never let the desire to please outweigh your responsibility to report accurately. Let's see integrity from a different perspective as well. In your simulations, you'll hit roadblocks, non-converging models, odd stress concentrations, unexpected behavior. And in these moments, it can be tempting to cut corners, tweak assumptions, ignore warnings, or apply questionable fixes just to get the job done. But shortcuts without justifications are dangerous. They can lead to misleading conclusions, or worse, unsafe designs. What's the better path? Be transparent. Document your choices. If you simplify something, explain why you did it, how it affects the results, and what trade-offs were made. Transparency always builds trust, not just with others, but within your own process as well. Another serious breach of integrity is misrepresentation, that is deliberately making results look better than they are, or hiding limitations. Whether it's to win a contract, avoid tough questions, or cover a mistake, it undermines everything engineering stands for. Integrity means owning your model, its flaws, limitations, assumptions, and uncertainties. Show the complete picture, your boundary conditions, your mesh, your solver settings. Don't just present what, explain the why. Integrity in FEA isn't just a professional ideal, it's a responsibility. So, stay sharp, stay ethical, and most of all, stay real. Okay, so far, we have talked about mindset, ethics, mentorship, and how our own brains can trick us. All of those set the stage, but now let's turn the spotlight onto FEA itself. And the very first step in any serious finite element analysis is understanding the problem. Here is the rule. Don't start modeling until you know the context. Start with purpose. Why are you solving this? What decision will the results support? Next, understand function. How does the system work? And if possible, where does it fail? Then get close to reality. Look at the real assembly. Talk to people, technicians, test engineers, operators. They know the weak points better than any model ever will. Now check the CAD model with a critical eye. What's simplified? What is missing? Where are the joints? Where are the contacts? What is bonded, bolted, or free to move? Then identify material behavior. Are you dealing with ductile failure, brittle one, fatigue, temperature sensitive behavior? Then loads and constraints. What's applied? What is prevented? Is it thermal, dynamic? How about transportation? How about multiple load cases? Then define the overall physics of the problem. Is it structural, thermal, coupled, modal, transient? Now decide what outputs matter. Stress, deformation, temperature, pressure. Remember, not everything you can plot is something you should use for the outputs. Then set the accuracy target. Do you need a rough estimate or a high confidence value for safety, performance, or design sign-off? And finally, before you press solve, can you predict the outcome even roughly? That's how you build intuition and catch mistakes early. Okay, in this long list, let's zoom in on two items that deserves extra scrutiny here. First, physics, or in other words, choosing the right type of analysis. FEA isn't one tool, it's a toolbox of solvers. And each solver exists because it answers a different kind of physics questions. So instead of clicking a static structural out of habit, let's choose the analysis type with intention. Let's begin with a simple question. Does time matter in this problem? If loads and responses are essentially constant, a static analysis may be enough. But if anything evolves with time, a ramp load, an impact, a thermal cycle, then you need a transient analysis. Next, even if time variation is not the main issue, vibration still might be. If dynamic effects matter, Start with modal analysis to find natural frequencies and mode shapes. If the system is excited continuously, harmonic response captures a steady oscillation. And if the excitation is irregular or noisy, random vibration is often the right choice. Now, let's talk about the stability. Ask this question: could the structure suddenly lose stiffness and change shape dramatically? This could be due to buckling. So, if buckling is a concern, eigenvalue buckling gives a quick estimate, but when imperfections, contact, and post-buckling behavior matter, nonlinear buckling is the more realistic approach. Now, shift your attention to temperature. If heat transfer affects performance or stress, you may need a thermal analysis. Steady-state thermal is for constant conditions. Transient thermal is for heating and cooling over time. And sometimes the real problem refuses to stay in one box. If one field drives another, like thermal expansion creating stress, electromagnetic heating raising temperature, or fluid loads deforming a structure, then you're in a multi-physics territory and you need a coupled analysis. I also want to mention that sometimes problems belong to other things like CFD, mass transport, or optimization studies, not in a purely structural analysis. That's why software like ANSYS offers so many analysis systems. They are not extra features, they are different answers to different engineering equations. And now, after you choose the analysis family, you make the next critical choice. Will the model behave linearly, or do you expect nonlinear effects? Because linear versus nonlinear is not a separate topic. It can actually show up in all the analysis systems that we have covered so far. We will cover nonlinear analysis in future sections of this series. Now let's talk about outputs, because the outputs you choose should come directly from the question you're trying to answer. Let's start with the most common one, stress distributions. If your concern is yielding, fracture, or failure, stress is often the first output you look at. Remember though that stress itself comes in different flavors, like principal stresses, von Mises stresses, also known as equivalent stress or shear stress. But sometimes stress is not the main story. Sometimes the story is shape change. That's when you focus on displacement fields to check deflection, alignment, clearance, and fit. And once you know how the model deforms, you often need to know what the supports feel. That leads to reaction forces, critical for sizing balls, brackets, bearings, and anchors. Though in many cases, for these items, just hand calculations should be enough. Now, if your system vibrates, your output change completely. You may need natural frequencies and mode shapes to understand the dynamic behavior before you even think about the stresses. And if temperature is involved, you shift the game. Now you're looking for thermal gradients and often thermal stresses that come from expansion or contraction and constraint. For slender structures, another output becomes central, buckling capacity. Not how much does it bend, but when does it become unstable. Sometimes the output is not a field at all. It's a single engineering design number, for example, a factor of safety, based on a chosen failure criterion. And in more advanced problems, the outputs go beyond simple stress and displacement. You might need fatigue life predictions for repeated loading. You might need residual stresses from welding, forming, or prior load history. You might track damage accumulation as the material degrades. Or you may care about contact pressure between the mating parts. And yes, I know, there are many more. But here is the catch. Not every analysis type can produce every output on this list. So before you build the model, be clear about what you expect to extract and what you will use it for. Now that we have clarified the problem, the physics, and the outputs, we're ready for a really important question. That is, do I even need FEA to solve this problem? You'd be surprised how often students come to me with an FEA model and ask for help, when all they needed was a basic static analysis or a quick hand calculation. And my first question is always this: why FEA? Because here is the truth: FEA isn't free. It takes time and effort. And if done poorly, it can lead you down the wrong path with a false sense of accuracy. This false certainty often comes from a halo effect around FEA. Because the tool is powerful, we assume every output is right. So every time you have a problem in hand, before modeling it in FEA software, ask yourself, can this be solved using basic free body diagram and mechanics of material calculations? I know this example is for structural problems, but you get the idea. If the answer is yes, FEA might not be needed. Also, you can ask, do I really need fine-grained stress field or displacement data? Or you can ask, is there something in this problem like geometry, loads, or other boundary conditions that are complicated? If the answer to either of these two questions is yes, then go ahead, use FEA. But if a simple hand calculation gets you there faster and more reliably, go with it. In engineering, simple and right beats complex and wrong every time. Okay, since this video is on practical tips in FEA, from now on we assume that we need to use FEA for the analysis we have in hand. So far, we have discussed the type of analysis and the outputs we expect from it. The next step is to make sure we have a clear objective. And that means going beyond just running a simulation. We need to ask what exactly we are trying to achieve with this model. This is where a SMART framework comes in. The objectives must be specific, measurable, attainable, relevant, and time-bound. First, let's focus on a specific. If we want objective to be a specific, we want to know, what do I want to learn? Is it maximum stress, displacement, factor of safety, or fatigue life? A specific means the objective tells you exactly what output matters and why. Next, the objective must be measurable. How will I quantify success? Do I have clear numerical targets or threshold in mind? A stress limit, a deflection tolerance, a minimum frequency, a target safety factor? Then, the objective must be attainable. Is my objective realistic with the model I can build? Do I have the necessary data about physics, boundary conditions, and material properties? And also, do I have the right equipment to actually run these simulations? After that, the objective must be relevant. How does this analysis serve the bigger picture? Will the results actually inform a design change, a safety check, or a compliance requirement? And finally, the objective must be time-bound. When do I need the results? Do I have enough time for verification, validation, and maybe even more iterations? One day forces a different strategy than 1 month. Defining SMART objectives will keep your analysis focus grounded in engineering reality and tied to real decisions. Otherwise, it's easy to get lost in the details and lose track of why you're running the analysis in the first place. Let's look at an example to show the difference between a very poor and a well-defined objectives. For this example, I'll focus only on the first two letters, S and M, a specific and measurable. Imagine we're analyzing a pressure vessel. Depending on how we phrase the objective, the clarity can vary a lot. A very poorly defined objective might say, to determine if this design will work. But what does work even mean? Does it mean no leaks? No mechanical failure? Under what conditions? It's too vague. A step-up objective, but still a poorly defined one, can be to determine if the pressure vessel will break. Okay, that's better, but it's still too broad. Break under what kind of loading? What failure criteria? And where exactly? Now, let's make it better. A fairly defined objective states to determine the maximum stress in the pressure vessel at 4,000 psi internal pressure. That is more specific. We've got the load defined, but it is still not fully measurable because we haven't defined what stress means in a precise, reportable way. Is it von Mises, principal stress, membrane stress? And finally, a typical specific and measurable objective is to determine the maximum von Mises stress at any point in the pressure vessel under a static load of 4,000 psi internal pressure. Now we have both S and M. It is specific because the loading condition is clearly defined, and it is measurable because the output is unambiguous. It is the maximum von Mises stress. This was just an example. As you know, real projects often need even more details in the objective statements. Clear objectives drive every modeling decision, from meshing to post-processing. So, if you can't state your objective in a way that are specific and measurable, you're not ready to build the model. Let's talk about one more important topic before we end section 1 of this series. I want to talk about analysis paralysis. So far, we have covered a lot of ground on what to think about before you starting your simulation, understanding the problem, choosing the right type of analysis, and defining objectives. But you cannot stay in this phase forever. Yes, you need to understand the problem, but at some point you need to start as well. Build the model, run something, see what breaks, fix it, improve it. Overthinking, that is trying to make everything perfect before clicking solve, can hold you back more than any technical challenge. That is called analysis paralysis. In FEA, even after modeling starts, analysis paralysis shows up like endless mesh refinement or tweaking boundary conditions again and again without solving once. It feels like diligence, but it's really fear of being wrong. So, how do you break free from analysis paralysis? First, set a time limit. Give every phase a stopping point. Next, get feedback early. Someone else might spot the issue faster. Then, define good enough. Know what level of accuracy is enough for your purpose. After that, iterate, model, solve, fix, repeat. And finally, accept uncertainty. You'll never eliminate it all, and that's okay. The goal of FEA isn't perfection, it's decision making. So move forward with clarity and let progress guide you. Alright, that's it for the first section of the FEA Done Right series at MechCADemy, where we ask big questions even before we hit solve. Now, let's go into an actual FEA. I'll start with a quick review of the basic terminology and theory behind FEA in section 2 of the series. See you soon.